Let me briefly introduce myself. My name is Soo-hyun Lee and I am doing my research in the Advanced Opto and Nanoelectronics Laboratory with Professor Jung-Hoon Kwak. My study subjects are about the analysis on the operational mechanisms of the organic and quantum dot LEDs and their applications. So the topic I'll introduce you here is quantum dot and organic hybrid light-emitting diodes with reduced process steps for full-color displays. First, I'll explain some challenges on QLEDs, the motivation for this work, and some experimental details as an introduction. Next, specific fabrication method for full-color light-emitting device will be shown with a schematic illustration, followed by the experimental results and discussion about them. Finally, I'll briefly summarize this work. QLEDs are well known as a promising candidate for the next generation display devices, especially due to their excellent color purity and easy color tunability by simply controlling the dot size. Also, the QLEDs share similar device structure with OLEDs, which have each charge transport layers, electrodes, and an emitting layer. However, it has been the most difficult challenges for QLEDs to pattern the EML, because the cuties in the EML are usually deposited using colloids, forcing the fabrication process to contain the solution process. In other words, the charge transport layers under the cuties can be easily damaged during the patterning process. Although the solution process has several advantages such as low cost, simple process, and large scale manufacturing, it has been a serious obstacle for QLEDs to be realized in the industry at the same time. Several studies on the patterning techniques were conducted so far. In chemical ways, photolithography is one of the most common and famous methods in solution processed devices, which accompanies photoresist deposition and washing process. And physically, the inkjetting is famous for efficient material usage and the merit for drop-on-demand technique. However, these methods usually contain complex and high-cost process with some additional specific techniques. Most of all, it's going to be difficult more and more to pattern each subpixels as the resolution of the display gets higher. Therefore, it is demanded that efficient and simple patterning technique need to be ensured for solution process high-resolution full-color display. As shown in the figure, QLEDs are composed of several layers, and a common layer indicates the layer deposited in each pixel in common. Thus, it usually indicates the charge transport layers inside the QLEDs. But if we can use a common color emitting layer, we can reduce one patterning step for the color. So here, we adopted a blue common layer, the BCL, which has a role of second electron transport layer in the red and green subpixels and the emitting layer in the blue subpixel. Using this method, we can skip a patterning process for the blue subpixel without any additional complex skills, because the BCL consists of organic materials which can be thermally evaporated like any other common charge transport layers. As materials for the BCL, we used BCBP with a wide band gap as a host and BCVBI guest as a fluorescent dye. These are widely used materials in fluorescent blue emitting OLEDs and have well-matched energy levels with the other materials used in our devices. And here are the device structures we fabricated. Devices R and G denote red and green emitting QLEDs, and devices RC and GC refer to QLEDs adopting the BCL. And the device B denotes blue emitting OLED using the BCL as an EML. The rest of charge transport layers and electrodes are same. As explained previously, we designed full-color hybrid light-emitting device using QLEDs as red and green emitting devices and an OLED as a blue emitting device sharing the BCL. The figure shows the schematic illustrations of the full device fabrication process, including all red, green, and blue subpixels. First, an HIL and HTL are common materials for all subpixels, so that they can be deposited by the solution process on the indium tin oxide electrode, which is pre-patterned onto the glass substrate. Next, the red and green colloidal QDs are also deposited by the solution process onto each red and green emitting subpixel area, forming EMLs of QLEDs. For the blue subpixel, the thermally evaporated BCL forms an EML in the blue emitting area, deposited directly on the HCl. At the same time, because the BCL covers the entire area without any mask or patterning techniques, it is also stacked on the QDs and plays a role as the second ETL in the red and green emitting QLEDs. Finally, the full-color hybrid light-emitting devices are generated by the thermally deposited ETL and cathode. By using this strategy, only 2 steps of patterning process are required for the full-color device demonstration consists of 3 colors of red, green, and blue without any complicated skills. For the HTL and ETL, we chose PVK and TMP-YPB. Because the TMP-YPB has much higher carrier mobility than PVK, we can locate the exciton generation zone near the HTL. If so, the blue side emission at red and green subpixels can be sufficiently suppressed. This slide shows the JVL characteristics and efficiency of the devices. The current density of the device B is much higher than that of QLEDs right after the device is turned on, whether the BCL is inserted or not, which may be attributed to relatively shallow HOMO level of BCD VBI, inducing direct hole injection from the HTL to the EML. But in case of QLEDs, it is difficult for holes to be injected from the HTL to EML due to deep valence band maximum of QDs. Furthermore, the carrier mobility of QDs is significantly low, which means that the thickness of the QD layer directly affects the current flow through the device. Due to the slightly thicker EML in the QLEDs compared to the OLED, the red and green emitting QLEDs shows higher turn-on voltage. In addition, as the BCL is inserted between the QD EML and ETL, the electron injection from the cathode is hindered by the increased electron injection barrier and low electron mobility of BCL. So the BCL adopted devices RC and GC have little bit increased turn-on voltage. Nevertheless, they reached higher peak luminance and efficiencies, implying improved charge balance in the EML. The external quantum efficiencies increased about 12 and 38% for the red and green emitting QLEDs, respectively, by adopting the BCL. Further, the device B exhibited its maximum EQE, which is comparable to conventional OLEDs adopting BCD VBI as a fluorescence emitter. In the first figure, the EL spectra of devices adopting the BCL were drawn with solid lines, while those without the BCL were drawn with dashed lines. It is quite important that the EL spectra of the red and green emitting QLEDs were almost unchanged despite of the presence of the BCL. As clearly shown in the expanded EL spectrum, although the device RC and GC exhibited very small amount of emission induced by the BCL, it is suppressed enough to maintain the excellent color purity of QDs. As a result, the color coordinates of red and green emitting QLEDs are hardly shifted when the BCL was inserted, and the color space consists of device RC, GC, and B covered 97% of the space consists of device R, G, and B. Further, we demonstrated a full color QD and organic hybrid LEDs on a single substrate, as shown in the videos. These are driven with a current density of 1 mA per centimeter square for each pixel. For the previous results, we attribute the device performance enhancement of red and green emitting QLEDs to two reasons: improved charge balance and the energy transfer process. First, when we fabricated electron-only devices for the red and green emitting devices, EODs adopting the BCL showed much lower current density compared to those without the BCL. As a result, the current densities of the device RC and GC are lower than those of devices R and G, as shown in the JV curve of full devices. Thus, considering the mobilities of the ETL and HTL, improved charge balance was achieved by reduced electrons. It also matches well with the reduced electron mobility and increased electron injection barrier by the BCL, as shown in the energy level diagram. In addition, we examined the transient electroluminescence response of the devices. For equivalent testing environment, we applied the voltage pulse having amplitude corresponding to 300 kL per meter square for all devices with a repetition rate of 100 kHz and observed the electroluminescence response. By observing the time resolved EL at each of their EL peak, it is shown that when the BCL is employed, the EL decay time is prolonged in both red and green emitting QLEDs, which implies that the radiative recombination in QDs was enhanced with the use of the BCL. We also fabricated the device GC prime, which has same device structure with the device GC, except the thinner QD EML, to intentionally generate the blue side emission to investigate the EL decay time at the blue band emission. We confirmed that the decay time at the blue band emission was shorter in the device GC prime compared to the device B. These results obviously indicate that the FRET process occurs due to the strong interaction between QDs and adjacent fluorescent molecules directly deposited onto them. Therefore, as shown in the illustration, the QD EML can be excited by two routes: direct injection of charge carriers and energy transfer from the BCL to QDs inside the electrically driven QLEDs, leading to the enhanced performance. In summary, QLEDs must contain the solution process, so there have been some difficulties in patterning the QD emitting layer. As one solution, we suggest an organic blue common layer to reduce one patterning step for the blue subpixel and fabricate the QD and organic hybrid LEDs, which were demonstrated on a single substrate. The color shift by the BCL was almost negligible, so that the great color purity of QDs were maintained. Moreover, as an additional benefit, the energy transfer process was observed and the performance of QLEDs were improved. We believe that this new strategy will be helpful to effectively pattern the QLED and reduce tech time for the practical application as a future display technologies. Thank you for your attention.